My name is Katlynn Vicuña, and I'm currently enrolled at Kapiolani Community College in UH Manoa. I'm pursuing a degree in aerospace engineering. I'm presenting my project on designing a vehicle to collect debris to minimize threats to existing and future space missions and technology. My objective is to bring science and engineering together to resolve this problem. First, the science to fully understand my problem and its effects, then the engineering to evaluate our scientific data and implement a plan to resolve it. To summarize what some of the leading world space agencies have evaluated, we have launched over 9,600 satellites. There are over 22,000 objects floating around that we know about. Total mass of all these objects is about 8,800 tons. There's no way of knowing how many objects are actually out there, but statistical models show 34,000 additional objects greater than 10 centimeters, 900,000 objects smaller than 10 centimeters, and then there's calculated to be 128 million pieces smaller than 1 centimeter. So what is all the space junk? There's a wide variety of space junk out there. Here are some examples. Derelict spacecraft such as the United States Vanguard 1, it and its upper stage of its rocket are currently the oldest man-made objects still in orbit. Satellites being one that is in constant use, and in the news, an example being Starlink satellites that SpaceX has launched. Rocket boosters floating around from various missions. There's also random objects floating around that were lost on missions, such as gloves, thermal blankets, and cameras. Then on top of all that, there's terrestrial debris that humans didn't even put there. So here's a screenshot from Space Debris by Eric Gregerson with Encyclopedia Britannica. To quote directly, he says, "Space debris can cut through metal like a hot knife through butter. When two pieces collide, the two pieces now can turn into 10 pieces, increasing the number of pieces of debris in orbit, causing a higher probability for impact and potential damage. The ISS was just recently impacted by a piece of debris that was not categorized as a known piece of space debris. Luckily, nobody was hurt, but it caused for oxygen to escape and a panic and cost money to fix. All this debris is going to interfere with launches to other worlds. Anytime we have launched something, we have to calculate the position of space debris to have a successful launch. This window will get smaller and smaller as time goes on and more junk is collected into orbit." So, this is where the engineering phase comes into play. How are we going to solve this issue? The next phase in challenge is to design and implement a spacecraft to somehow collect or nudge the space junk. This is an animation of a CubeSat, courtesy of Hawaii Spaceflight Laboratory. A CubeSat is a small scientific instrument already being utilized for a variety of different types of experiments. The Artemis CubeSat kit is currently being constructed to provide a cost-effective way for students to be exposed to space missions. Everything is needed to power, control, and detect the location of a CubeSat is confined in this apparatus. They come in many sizes, but generally a 1U CubeSat is 10 centimeters by 4 inches on all the sides. The idea behind what I call the muscle will be a customizable shell for these pre-existing spacecraft to turn a single-purpose mission into a dual-purpose cleanup mission. Another decision that needed to be made was the type of material to use for the shell. Here are some of the more common materials used in 3D printing. All these materials would burn up upon re-entry. Once a design was made, an open source file could be released, and depending on whatever material is optimal for the user, they could print accordingly. For the print based on recyclability, toxicity, heat resistance, strength, cost, weight, and overall just easy for us to get, factoring all in for this project, PLA was our number one choice. So here's the designing phases for the muscle. Column 1 shows recycled cardboard to start an initial design process. Column 2 shows some variants. The corners have been cut off and then the edges were chamfered, still to maintain structural integrity and to accommodate for more cube to junk. Column 3 is CAD design. Column 4 is a 3D print. To launch a CubeSat, there needs to be an implemented deorbit plan, as not to add to the amounts of pre-existing space junk. So why not try to take out a piece of space junk in the process if possible? Larger pieces of space junk can be tagged in categories for different types of removal. Mid-size can possibly be nudged or pushed into orbit to be burned up upon re-entry. The small debris potentially may be collected later. The mid-size is what the muscle is looking to collect and tackle first. Shown here on the top is a neutral buoyancy lab that NASA uses. The diving tank is 202 feet long, 102 feet wide, and 40 feet deep. It contains 6.2 million gallons of water. It's a full-size replica of the International Space Station. Since it's very difficult to recreate space conditions, the closest is underwater to mimic the lack of gravity, and overall cheaper than some of the other experiments that they have used. Since I did not have access to the actual buoyancy lab, I utilized what we do have, and I come to call it the Pacific Neutral Buoyancy Lab. Here's a screenshot of the testing video. After initial tests, it was found that a few minor adjustments and some more testing will be needed to be made, but overall shows promising results. Based on analysis, there will be needed to make some design iterations to account for more of the round or flat debris pieces that did not easily adhere to the shell with more testing. Thank you for listening, and thank you for Anchor for this opportunity.